This video is an introduction to the Z-transform. It's the first of several videos covering material from Chapter 10 on the Z-transform. The Z-transform is a generalization of the discrete time Fourier transform, or DTFT, analogous to the way the Laplace transform of Chapter 9 is a generalization of the continuous time Fourier transform. In fact, Chapter 10 will use many of the same concepts and methods as Chapter 9 and will be very similar in its format. Like the Laplace transform, the Z-transform extends the reach of Fourier analysis to unstable signals and systems. Thus, the Z-transform may be used for both stable and unstable signals and systems. We'll also see later in this chapter that the unilateral Z-transform is useful for systems that are not initially at rest. In other words, systems that have initial conditions. Here is the Z-transform in its formal description. It basically converts a discrete time sequence x of n, over here on the left, into a function of frequency x of z on the right. And the way it does this is by doing a summation of the sequence x of n times z to the minus n. And we sum that from n equal minus infinity to positive infinity. We'll talk more about what z is later, but for now, z is a polar complex number that has both a magnitude, absolute value of z, and a phase angle represented by e to the j omega. So in the time domain, we have our sequence x of n. We will be doing the Z-transform to convert this into its frequency domain counterpart, x of z. And we'll see on the next slide in more detail how the Z-transform is related to the discrete time Fourier transform. In fact, the discrete time Fourier transform is just a special case of the Z-transform when the magnitude of z is equal to 1. So before we look at examples, let's learn a little bit more about the Z-transform. So first of all, what is z? Well, z is a complex number that has a magnitude, absolute value of z, and a phase angle, omega. So we look at z in polar form, not in rectangular form. And we can plot z as a quantity, a complex quantity, in the z-plane. So the z-plane has a horizontal axis, which gives us the real part of z, and a vertical axis, which gives us the imaginary part of z. So z can be thought of as a vector in this z-plane. The length of the vector, or its magnitude, is z, absolute value of z, and the angle, or phase angle of z, is given by omega. So we have z is equal to absolute value of z, which is the magnitude, times e to the j omega, which contains the phase of z. We will be dealing with z to the nth power. So if we take our definition of z here in polar form and raise it to the nth power, we can distribute this n inside the parentheses, and we get the magnitude of z to the nth power times e to the j omega times n. All right, so the magnitude part out here is a real quantity that either grows with n or shrinks with n, depending on its value, if it's greater than or less than 1. The e to the j omega n portion can be expanded out using Euler's formula into cosine omega n plus j sine omega n. So one way to visualize z is by looking at the three cases where the magnitude of z is equal to 1, less than 1, or greater than 1. So for the case where the magnitude of z is equal to 1, we get, this is just a 1 out in the front here. So if we were to plot the real part of z, which is this cosine function here, we see that the real part of z then just becomes an oscillating function equal to the cosine of omega n. However, if the absolute value of z is less than 1, we have a shrinking envelope out in front of the cosine term here. So this now z becomes a shrinking or decaying sinusoidal function, a decaying cosine function. And then the last case where z is greater than 1 in magnitude, we have the opposite. We have the magnitude is increasing with n Thus, we have sort of an exponentially increasing sinusoidal function. So this is a nice way to graphically visualize what z is. All right, let's look a little bit more at the relationship between the z transform and the discrete time Fourier transform. So here are the definitions of both of these transforms here. So the z transform, remember, we take the sequence x of n and we multiply it by z to the minus n and sum over all n. Well, remember that z is equal to the magnitude of z times e to the j omega. So if I make that substitution here for z, I get this form over here. I get x to the n times magnitude of z to the minus n times e to the minus j omega n. Well, let's compare that with what we learned in chapter 5 on the discrete time Fourier transform. The discrete time Fourier transform, x of j omega, is the summation of the sequence x of n times e to the minus j omega n. Well, notice that these two forms are exactly equal to each other for the special case where the magnitude of z is equal to 1. In that case, the z transform is actually equal to the DTFT. Now, what this means in the z plane is that the Fourier transform corresponds to the z transform only along the unit circle where the magnitude of z is equal to 1. So the DTFT corresponds only to this special case of the unit circle in the z-plane. However, the z transform will use the entire z-plane. So this is another way of seeing that the z transform is a more general version of the discrete time Fourier transform. Therefore, the z transform is more powerful and we can do more things with it. So now let's take a look at an example of the z transform. The most important signals or sequences are exponential sequences because these are solutions to the linear difference equations which describe discrete time LTI systems that we're dealing with. So we're going to do the z transform of a real exponential sequence. Mathematically, this is x of n is equal to a to the n times the step function u of n. And what we're going to do here is assume that a is a real and positive quantity. However, this is just for this example, and our results actually apply to both complex and negative values of a as well. So the two different examples here we can consider is when a is between 0 and 1, we have a decaying exponential function. And remember, it starts at n equals 0 because of the step function attached to it. So this is what's called a right-sided sequence. It goes to the right with n. The other possibility is that if a is greater than 1, then when we have a to the n, this is going to increase as n increases. So we're going to have an increasing exponential sequence as shown over here, which is, again, a right-sided sequence. All right, so let's take the z transform of this. So what we're going to do is take our definition of the z transform. X of z is the summation of x of n times z to the minus n, and we'll plug in for x of n our sequence here. Now, one thing that happens here is x of n is obviously equal a to the n, which we'll plug in there. The step function basically means our summation is going to start at 0 and go to positive infinity. So we can change the limits of our z transform here from n equal negative infinity to n equals 0, because that's where our sequence actually starts. Now notice we have a to the n and z to the minus n. So both of these terms have a common exponent n. So let's factor out that n and write it as a times z to the minus 1 to the n power. And z to the minus 1, of course, is just 1 over z. So I have the summation of a over z to the n. Now, we can evaluate this using the useful infinite sum formula, which is shown here. The infinite sum formula says that if we have an infinite sum from n equals 0 to infinity of some quantity alpha to the nth power, then this sum converges to the value 1 over 1 minus alpha. As long as the magnitude of alpha is less than 1, we will have convergence. So let's apply this to our result here for our z transform. So x of z is the sum of a over z to the n. So using the infinite sum formula, we have 1 over 1 minus a over z. A over z, by inspection here, is our alpha in the infinite sum formula. We can clean this up. We've got a fraction inside of a fraction, so let's multiply top and bottom by z. So we end up with z over z minus a. And remember, the region of convergence is magnitude of alpha has to be less than 1. So in our case, we have the magnitude of a over z is less than 1. We can rewrite this in terms of z as saying that the magnitude of z has to be greater than the magnitude of a. So here is our solution. Here is our z transform. X of z is equal to z over z minus a, and the region of convergence, or ROC, is magnitude of z is greater than a. All right, so what we can do here is something similar to what we did in Chapter 9. Let's construct a pole zero ROC plot, which by now you're good at doing, but things are a little bit different here in Chapter 10. So first of all, let's go ahead and find our poles and zeros. So we have a 0, but remember, by setting the numerator equal to 0, we see that when z is equal to 0, we have a 0. So I'm going to plot that 0 right here at z is equal to 0 at the origin. We can find the pole very easily by looking at the denominator, setting that to 0. So notice I have a pole at z equals a. So in this first case, let's assume that a was a was between 0 and 1. So a is going to be somewhere inside the unit circle. Here's the unit circle shown in blue. A is somewhere between 0 and 1, so let's just place it right here. Now, our region of convergence, remember, is the magnitude of z is greater than the magnitude of our pole. So what this ends up doing here is our region of convergence becomes everything outside of this circle, which has a radius of a, which is equal to the pole, because we're dealing here with the magnitude of z. Remember that we can think of z as a vector. So the region of convergence is this shaded region outside here. With z transforms, region of convergence are always circular regions, whereas in Chapter 9 with a Laplace transform, we saw that the regions of convergence were always vertical strips. So that's one major difference here between Chapter 9 with Laplace transform and Chapter 10 with the z transform. The other thing I can just comment on here is that notice that the region of convergence includes the unit circle here. Well, that means that the discrete time Fourier transform must exist, because remember that the Fourier transform corresponds only to regions right on the unit circle. So since the unit circle is inside the region of convergence, that means the Fourier transform exists. And the reason for that is that this sequence here is decaying with time. It's you can think of this as a stable, well-behaved sequence that doesn't diverge. The other case here, let's say a was greater than 1. Remember, that's this case here where we have an increasing exponential sequence. Well, the only difference now is that our pole, z is equal to a, is going to be greater than 1. So our pole is going to be outside of the unit circle. But we still have our region of convergence is everything outside of this pole. So notice now the region of convergence out here does not include the unit circle. So this is a case where the discrete time Fourier transform does not exist. So in other words, if we take this sequence here and try to do a Fourier transform analysis of it, we can't. There is no way to do the Fourier transform sum to figure out what the transform is. It doesn't converge, and therefore we can't use Fourier analysis for the signal. But we can do z transform for the signal. Again, this is just pointing out one of the powers of the z transform compared to the Fourier transform. We can use it for unstable signals and systems, such as this example shown here. Okay, a couple more exponential sequences that are going to be useful to us in this chapter are left-sided exponential sequences. In other words, they start at 0 and they go backwards in time to negative values of n, like these examples shown here. So instead of going through all the details of deriving this, I'm just going to show the results here. But keep in mind that the way to actually derive these results here are following the same methods that we showed on the last slide. So we will save some time, and I'm just going to show you the results here. This first one is a to the n times u of minus n. So this is a step function with a time reversal. We have a minus n here as the parameter of the function. So this sequence starts at 0 and goes backwards to negative values of n. And again, a can be between 0 and 1, or a can be greater than 1. We get these two cases here. In this case, the z transform is negative a over z minus a. And another difference here is the region of convergence is absolute value of z is less than a. So what ends up happening here, instead of the ROC being outside of the pole, the ROC for left-sided signals or sequences is inside of the pole. So we have this shaded region here inside of the pole at z equals a. Notice this example, a is less than 1, so the region of convergence does not include the unit circle. For the case where a is greater than 1, the pole is outside of the unit circle, but again, notice the ROC is everything inside of this pole. And as always for z transforms, we see that the ROCs are circular regions in the z plane. A related sequence that's also going to be very useful to us is basically the same one as up here, except it's shifted over to the left by 1. So it has a step function u of minus n minus 1. So this one starts at n equals minus 1 and goes to the left in both of these cases. And its z transform is given by negative z over z minus a. And again, the ROCs are inside of the pole. All right, here's our last example in this video. So in this one, we're going to have a signal or sequence here that has two terms, and we're going to end up with an overlapping region of convergence. So suppose we have a sequence x of n is equal to 1/2 to the n times u of n plus 3/2 to the n times u of minus n. So this first term here corresponds to a right-sided sequence, one that starts at 0 and goes to the right, in other words, positive values of n. The second term, however, is a left-sided sequence because of the time reversal in the step function. So this second term here starts at 0 and goes backwards to the left to negative values of n. All right, so what we're going to do here to figure out the z transform of this sequence is to use the results on the previous slides, which I've shown here in this box here, and we're going to take the z transform of each term separately. So for the first term, we have a right-sided sequence. We're going to use this particular z transform pair, which we just went through in detail a couple slides ago. So this first term here on the left gives us z over z minus 1/2. You can see that a is 1/2 here. And the ROC, since it's right-sided, z is greater than a, or z greater than 1/2. Now, for the second term, we have a left-sided sequence, and its transform pair is shown right here, the second one here. Remember, there's a minus sign out in front there. So the transform of this left-sided sequence picks up a minus sign, which is shown right here. So we get negative 3/2 over z minus 3/2. Here, by inspection, we see that a is equal to 3/2. So for the left-sided sequence, the region of convergence is z is less than the pole, which is z less than 3/2. Now, this is similar to what we did in Chapter 9. When we have two regions of convergence, we have to make sure that the overall region of convergence satisfies both of these conditions. In other words, the overall region of convergence has to be the intersection of these two regions of convergence. So this leads us to our result. The region of convergence is that z has to be in between 1/2 and 3/2. And we'll plot this shortly. All right, so here's our result. Let's rewrite it here. And one thing we can do here is combine these two fractions by using least common denominator. And we end up with this expression here. I won't read it off since it's kind of lengthy. But one thing we can do even further is we can factor the numerator, which is not trivial here because we can't do it by inspection, but we can use the quadratic formula to write this in terms of its roots here. This allows us to determine the zeros of our z transform. Remember, the zeros are the two roots of the numerator. And so in this case, you can see that the zeros actually are complex quantities, and they are plotted down here in the z-plane. There's a 0 here and a 0 down there. So one of the zeros is at 3/2 plus j times root 3 over 2. The other 0 is at 3/2 minus j times root 3 over 2. You can see the two zeros, when they're complex quantities like this, they are complex conjugates of each other. More importantly, though, are the location of the poles. And the poles, we see one pole is at z equals 1/2. That's plotted right here. And the other pole we can see is at z equals 3/2, which is plotted right here. Now, remember, the region of convergence is z, magnitude of z, in between these two poles. So what we end up here is a shape called an annulus, or it looks like a donut, basically. This is the region of convergence between these two poles. Also, note that the region of convergence does contain the unit circle, because the unit circle, where the radius is 1, is right inside of this region of convergence. Therefore, we can conclude that the discrete time Fourier transform does exist for this particular sequence here.